Ever wondered how magnetic forces emerge from the subtle dance of relativistic motion? Discover how Thomas' precession transforms standard Coulomb forces into intriguing magnetic effects. By delving into Lienard-Wiechert potentials and Lorentz force derivations, we see charged particles' motions laid bare. Relativistic kinematics underpin these subtle electromagnetic interactions. Observing from a moving test particle's frame reveals no conventional Coriolis force, only its antithesis. Thomas' precession generates effective pseudo-forces, challenging our expectations of inertial frames. Detailed analysis shows that the anti-Coriolis force matches the magnetic force. Mathematical equivalence emerges when mass factors cancel, confirming a deep connection between motion and magnetism. When anticentrifugal forces overcome Coulomb repulsion at femtometer scales, theory hints at parallels with the strong force. This surprising derivation bridges electromagnetism and nuclear binding. In mutual circular motion, derivations converge. Concluding remarks show Thomas' precession not only explains magnetic effects, but may illuminate the strong force's underlying nature.
The paper we're diving into today is The Magnetic Force as a Kinematical Consequence of the Thomas Precession by David C. Lush. Quite a mouthful, right?
Yeah, I had to read that title a couple times before it started making sense to me. But it's actually asking a really big question. Could the magnetic force, like the same kind of force we see in everyday magnets, just be a kind of side effect from the weird way space and time behave when things move really fast? Especially when you bring in something called the Thomas precession.
Exactly. And just for anyone who maybe hasn't thought about Thomas precession since physics class, or, ever, it's this rotational effect you get when a particle moves and accelerates at relativistic speeds, meaning near the speed of light. Basically, it makes the reference frames of moving particles rotate relative to each other.
And that's super fundamental. Lush's core argument is, what if the magnetic force, instead of being just one piece of Maxwell's equations, a kind of force on its own, is what you'd expect to pop up just from this kinematic twisting, this Thomas precession, as you switch reference frames?
Right. The significance here, and why I think it's actually pretty bold, is that it tries to demystify magnetism even further. Instead of electric and magnetic fields are two sides of the same coin, which is standard relativity, it goes, hey, maybe the magnetic force is what you have to see if you're tracking with all the correct frame rotations as charges get pushed around. It's like he's saying magnetism isn't its own thing. It's just the price of doing kinematics correctly in relativity.
So to unpack the main method a bit, Lush considers two classical charged particles, one acting as a source and not accelerating, like it's super heavy or maybe it's part of a wire so it can't move. The other's getting flung around by the electric field, the Coulomb force. He's walking through like, what does the observer who rides along with this test particle see? From her perspective, reference frames are precessing, twisting around, all because of the Thomas effect.
And what's wild is that when you tally up all the pseudo-forces she expects, Coriolis, centrifugal, Euler, like the kinds you get on a spinning merry-go-round, some are there, some aren't. Specifically, there's no Coriolis force in the source particle's rest frame, because from that particle's point of view, nothing's turning. This means, though, that an anti-Coriolis force has to be popping up somewhere, almost as compensation. And that's what, in the usual inertial frame, looks exactly like the magnetic force. Seriously, that connection feels so satisfying. Like, you almost want to high-five relativity.
I know! And it's not just a formal analogy. In his equations, the magnetic force in the lab frame is identical to this missing or anti-Coriolis force viewed from that precessing test particle frame. You can see the math. He even gets the mass dependence to drop out, just like the real magnetic force, which only cares about the velocity and the charges.
And, he doesn't stop there. He teases out, okay, if the Coriolis term gives you magnetism, what about centrifugal and Euler terms? Could they hint at the origins of the strong and weak nuclear forces? I mean, that's a hefty leap. But his argument is that at really high energies, like inside an atomic nucleus, there might be a Thomas precession-induced anticentrifugal force that could be, well, strong and always attractive. He goes as far as to do some quick calculations, comparing how it might stack up to the size of a nucleon. Spoiler, it's a bit too weak, but not wildly off.
He does admit that this isn't the last word, like it's just a start. There are things he hasn't calculated, like the effects of field retardation, so it's not perfect. But, the idea that maybe the deep forces of nature and all the fields we've cooked up, to Lush, maybe they're just labels we slap on the weirdness of special relativity plus classical kinematics when you're really strict about it.
There's something almost philosophical there, right? Like, is a force always a force? Or sometimes just the universe's way of bookkeeping as things zoom around with Einstein's rules?
For sure. And sometimes I wonder, like, if you could go back and tell Faraday or Maxwell, hey, what you thought was a core force of nature might just be a perspective effect if you're riding along with the particles, would they be delighted or horrified?
Ha!